All right, so this mini lecture is going to give us an idea about the resolution of lenses and mirrors. So I'm going to describe that near the end, but I want to back up and think about what resolution is and why we have to even consider it in the case of lenses and mirrors. And it's all because of diffraction. When we use lenses and mirrors, we use them in things like telescopes and microscopes, and we want to see really, really far away, really, really tiny things. And if they're really, really close together, these, like a star or stars or celestial bodies, these very, very tiny particles can exhibit or elements, stars, can show a diffraction grating inside of our telescope. And we want to make sure are we seeing two objects, or are we seeing the diffraction pattern, or what's going on? Same is true when we look at a microscope at something really, really tiny. Are we seeing two objects? Are we seeing a diffraction grating of one object? What's going on? And so we want to understand how diffraction gratings are, how we resolve objects, and in the sense that we have to consider diffraction. Okay, so we can think of a lens like a slit. Light goes through it, right? Like a slit. So let's go back to our single slit idea and remind ourselves a little bit about those principles of diffraction and how we get those central maximum and then the fringes, and then turn that into a circular slit and then apply it to the lenses. So that's our little road map. So again, remember, we want to look at two objects really, really close together. And are we seeing on a screen the manifestation of those two different objects, or are we seeing on a screen the diffraction? How do we resolve between two different objects? All right. So keep in mind, for a single slit, we know that the first maxima is at an angle where the sine of the angle is equal to the wavelength of the light over d, where in this case d is our slit width. And when we have that, we get those central maxima and those subsequent fringes. Now, if we're dealing with really, really tiny angles, so you can imagine, for example, celestial bodies where the object is really, really far away. If we're looking at the really, really tiny angles, theta is on the order of the sine of theta. This is the small angle approximation that we've used before, that perhaps you've used in other mathematical applications. Therefore, we get a representation where theta is equal to the wavelength of that light divided by the slit width. All right, so that's for a slit with very, very small angles. Now, what if the slit is circular? Well, if the slit is circular, we still end up with a central maximum. So let's say this is my central maximum. Then we get these circular fringes around it. So we still get a diffraction pattern, but it's in a circular shape with, as you might expect, with a central maximum and a circular diffraction. Now, just like with a single slit, that central maximum, the angular width of that central maximum is half of the angle of those, of the width of the slit. In a single slit experiment, the angular width of the maximum is half the angle of the slit for a single slit. A circular is somewhat different. We kind of have to do an averaging because that slit changes its size in a circular pattern. And so it has a factor. So it's not just theta equal to lambda over d, it's 1.22 times lambda over d. And this factor 1.22 is that width isn't uniform across its across the circle. The width isn't uniform across the circle. And so diameter, that's the word I'm looking for. It's not uniform across the diameter. And so we need to do some mathematical analysis on that. I'm not going to deal with here. That's been a really long time since I've dealt with that in more of an advanced optics class. And so we do know, however, that on average, it's an approximate, but on average that factor is 1.22 lambda. All right, so When two objects are very, very close together, we want to be able to resolve them. All right, when two objects are very, very close together, we want to be able to resolve them. And so you can imagine that if I have two objects producing light, that the central maximum may overlap. And if they overlap, it kind of looks like just one central maximum. So at what point do I see a separation of those central maximums so that I can resolve that there's two objects instead of just sort of this wider single object? Hopefully that makes sense. So if we were to imagine that we have two objects, and here's the profile of the first one, the diffraction gradient of the first object, and here's the diffraction gradient of the second object. And these two maximums, not great picture, but these two maximums overlap. I kind of just see these brightness, and how do I know if it's one object or two objects? Okay, so that's what we're dealing with when we're talking about resolution. You might imagine that this is somewhat dependent on the observer, how my interpretation of those central brightnesses, how bright it is. This is going to be, where these two overlap is going to be a little bit brighter, when they overlap a little bit less. Like, all of that's a little bit dependent on the observer. So you kind of have to normalize it. We have to give some representation of a normalization, and that is what we call the Rayleigh criteria. The Rayleigh criteria. No N. I'm going to make sure I spell it right. All right, so this criteria tells us that two objects are resolvable or discernible if the central maximum of one is at least overlapping the first minimum of the second. Okay, it can be further, but they're just discernible. Just discernible. We can just resolve that there are two objects if the central maximum of one overlaps the first minimum of the second. So basically, said another way, that none of their central maxima overlap. Okay, so the peaks of those central maxima don't overlap. So what does that kind of look like? So if I'm going to try to draw it, and as you can see, I have my growth opportunities and my abilities to draw. All right, so here's the central maxima of one. No problem going this direction. It would be if that central maxima of the second one overlaps here with the minimum of the first one. So pink being the first, blue being the second. That's when we say that they are just resolvable. Just resolvable. So if I have two celestial bodies, they're just resolvable if I get a diffraction pattern where I can see that the central maximum of one overlaps at a minimum, the central minimum, or that first fringe of the other one. Now, why is any of this important? Well, these would be for circular apertures, circular slits, so to speak. And a lens is like a circular split. It's circular with an edge, a boundary. And so this becomes very important for optical instruments. In the case of optical instruments, this diameter, or this D, is the diameter of the lens. Or the mirror, if we're dealing with a mirror. Right? So the diameter of the lens or the mirror. So this criteria becomes very important for us. This understanding becomes very important for us so that we can determine between celestial bodies or really, really tiny things in a microscope. All right? So it allows us to recognize whether or not something is one object with a diffraction pattern or two distinct objects very, very close together. All right, so we're just going to play with this a little bit. It's about real surface level for our particular use of this. We'll do a sample problem. You have a few homework problems. But the idea is that this is just an overview of this idea of resolving power, recognizing the Rayleigh criterion, and how it has use when we're dealing with optical instruments and really, really tiny things like microscopes, really powerful microscopes, or really, really far away things like really powerful telescopes. All right, good job.